All right, good evening, everyone. Happy New Year. I hope you're doing well. So tonight we have a really nice, quiet meeting. Like I said, it's home style. We have a bunch of members coming in to present, so that's going to be really nice, but nonetheless, very, very interesting and engaging. So on the menu tonight, I'm going to do an introduction. Literally, I'm going to take a few minutes to introduce myself as a new meeting chair. Then Dave's going to have his usual Ottawa skies for the month, and he's also prepared for us a special book report on the book Hidden Figures, and I'll let him tell you what it's all about. So it's a book, but it's also a movie, and the movie came out today, so you've still got some time to go see it. Then we've got Al Scott's 10-minute astronomy news. Then Gordon will present some observations, some spectroscopy observations based on Tim Cole's presentation from a few months back. Then we'll have a short break as usual, and in the second half, Simon Hanmer is going to give us a talk on the early Mars climate. So that's going to be another great talk tonight, and we have loads of observation reports, like I'm warning you. So we have some new members in the last month, some Christmas presents. So we have Brian Blake and Colleen Mahoney, Peter Dolan, Glenn Golden, Maya Meads and Patrick Meads, Ethan Solis Sanchez, Peter Juncker, Martin Jensen, and Etienne Rollin. Let's give them a warm welcome. All right, and these are all the new members from 2016. So I'm going to take a minute just to introduce myself. I don't have any slides. I'm just going to talk to you. So my name is Kellyanne Jordan. You may remember me as the girl who brought the cookies that one time. So I'm a CEGEP student over in Hull. I'm studying pure science right now. So I go to Heritage College, which is basically the only English CEGEP in the region. So I really love mathematics and physics. I have an interest for all science, but particularly astronomy. So in this club, I like working with people. I like starting projects. I like leading them. And I'm a very, very passionate person. So when I like something, when I love something, I love deeply. I'm always getting involved. I volunteer a lot. And so, especially with the RASC recently, it has been a really nice opportunity to get going. So I think people are wanting to hear my goals for the year, and I don't really have any. I've only been a member for a year, so I don't want to jump in and change everything around. However, what I would like to do as meeting chair is maybe increase the sense of community that we have, especially in these meetings and in everything we do, really to encourage working together and get everyone's opinions when possible. And I want to make these meetings ours and not just mine or, the few presenters who come back every now and then. I really want everyone to feel comfortable, to feel at home. When you guys chime in, make jokes, I love it. It can really be ours. And also I have the meeting chair address. You can write me anytime. Please, never hesitate. If you have questions, suggestions, if you want to discuss something, even if you have observations, if you took your first picture of the moon and you want to show it, then please, don't hesitate to do so. And let's have fun. For the year, I don't want this, I want this to be serious, but I don't want it to be too formal. I want to be able to have fun and have a nice experience with you guys. So like I said, relax the atmosphere. I said you guys can chime in. And please laugh when I make bad jokes. I would really appreciate that. So I really look forward to working with you all. I look forward to the GA. I look forward to meeting you all and sharing these meetings with you. So without further ado, we can welcome Dave Chisholm to show us the January skies.
Well, thanks, Kelly. So let's take a look at what's happening in the Ottawa skies this month. Here are the moon phases for January. and the full moon is on January the 12th. Mercury, the greatest western elongation, is on January the 19th, and look for it in the morning sky. Venus is visible in the evening sky, and we have a greatest eastern and greatest western elongation a few days apart there, a week apart. And Mars is visible in the early evening all month. I don't know if you looked up tonight, you could see a nice line between the moon, Venus, and Mars. Jupiter is visible in the early morning, and as we move towards the end of the month, you'll be able to see it in the late evening, early morning. Saturn is visible in the early morning. Uranus and Neptune are visible all month. Uranus is visible all month, Neptune is visible all month in the early evening. The iridium flare, I have to, as I did last month, I'm clarifying where to see the iridium flare for this particular report. If you're in Canada or you're out in Orleans, it is not going to be a minus 8.3 magnitude. It's a very point-specific observation. So this is if you happen to live at the corner of Kent and Nepean Street, you're the lucky one. And again, go to heavensabove.com, put in your longitude and latitude, and you can get an accurate report on this. Typically, it only looks out about 2 or 3 weeks. Luckily, the International Space Station is not quite so picky. So the best viewing date from anywhere in Ottawa is January the 15th, and early in the morning. There's where it goes across the sky there. And this is my cartoon of the month. Now we're going to move into an interesting video that I came across before getting into the book report. And if you're on Facebook, there's a group called Lost Ottawa where they collect lost pictures, old photos, old films, and so on. And somebody pointed me to one for the Dominion Observatory. And I thought it was interesting. But the confusing part is, take a look at the telescope that they're using. It's not the same telescope that is at the Museum of Science and Technology. So let's just take a quick look at this newsreel. There's no sound. This is 1911. So this is a telescope that is not the one that's at the Museum of Science and Technology.
And it's not under that dome.
Yeah, apparently it's a, what is it, a transit scope?
Transit dome.
Okay. I expect they probably were showing that in the movie theaters.
That was the one for coal burning, I guess, right?
Yes, yeah. Okay, so I'd like to do just a quick book review here on this book called Hidden Figures. I just completed reading this fascinating book just before Christmas, and it's about the human computers that were hired by the National Advisory Committee for Aeronautics, which eventually became NASA. The book called Hidden Figures was written by Margot Lee Shetterly, and it focuses on 3 women, Katherine Johnson, Mary Jackson, and Dorothy Vaughan, who were part of a group of black women hired in the mid-40s to work at the Langley Research Center in Virginia. When engineers needed to calculate trajectories, they would hand the calculations over to the human computers, who would determine the exact requirements for the astronauts to land safely within the range of the rescue ships. With the advent of mechanical and electronic computers, the women were still called upon to check the accuracy of the results, as the new devices were not 100% trusted back then. In fact, John Glenn insisted that Dorothy Johnson double-check the computer's calculations before he went up on his historic orbit of the Earth. As he said, he wanted someone he could look in the eye, and not an unfeeling machine when his life depended upon it. The book starts in the mid-1940s right through to the first moon landing, and shares the important involvement of the human computers in achieving all of NASA's successes. It also delves into the prejudices of segregation within the state of Virginia and at NASA. I've brought 2 copies of the book with me. One I've given to Estelle and will be available next month or the following month from the library. And there's one that's going to be part of the door prize tonight. Okay, and just before I hand it back over to Kelly, for those of you who subscribe to astronomy, there's a nice 6-page spread about the book and the movie in the February edition of Astronomy. Kelly.
Thank you, Dave. So I did see the movie today. I'm not good with words, but I'll do my best. It was fantastic. It was really good, first of all. So Dave told me that the book really focused on the racial problems within NASA with these ladies. There was a lot of racial tension, and there was still segregation in their state at that time. But I found the movie, while of course talking about racism, was very mathematical, and it really spoke to the scientific people in the room. You had a look at real situations and problems, especially from the Atlas mission, amongst others. So you got a real look at the rockets, and you got, sometimes the actors would explain the equations they were doing. So it really does cater to more scientific people, especially in a movie where the 3 main characters are women. I did expect it to be more emotional, but it's really great for mathematicians. So next up, Al Scott with his 10-minute astronomy news update.
Excuse me, I'm going to hijack this for a moment before you give us your update.
Okay.
Al wasn't with us last month, but those of you who were, say Al wasn't with us last month, but those of you who were will remember that he received a service award. So tonight I'd like to present it to him. Do we have the? Aha, the envelope, please. There we are. So I don't remember the list of accomplishments and things that Al has done for us. I know he was past president. I know he's run the loan libraries, telescope loan library for quite a while. And I know there've been lots of other things. So congratulations, Al.
Thank you.
Now it's yours.
Thank you, Gordon. And thank you, Kelly. And thank you all. And Happy New Year. Welcome.
Happy New Year.
Looking forward to a good 2017. Indeed. And on to the news. So some of my news today is going to be rehashes of things that I presented before. Maybe updates, interesting discoveries that have pushed these issues to the fore. Planet 9, I gave a talk a little while ago about some interesting discoveries that have been made by astronomers of distant Kuiper Belt objects on very odd orbits clustered together, which seem to have provided evidence that there's another major planet out there that we have not yet discovered as part of our solar system, on a very highly elliptical orbit, probably quite far away, perhaps as much mass as some of the outer gas giants. So astronomers now are trying to court fame and find this predicted 9th planet, searching the areas that it's predicted to be with the telescopes at their disposal. And they've discovered in this search another large dwarf planet, which was announced last year. The object was actually discovered in 2014, called UZ224, is 330 miles across and 91.6 astronomical units from the sun. Astronomical unit, for those of you who don't know, is the distance between the Earth and the sun. So it's almost 100 times further out than the Earth. This object, 330 miles across, is visual magnitude 23. So very dim at this distance. And it takes 1,100 years to complete a single orbit around the sun, making it the 3rd most distant solar system object known. So the search continues. We expect that a lot more will be found, and hopefully Planet 9 will show up soon. Exciting times. Another one that I talked to you about, Tabby's star, or the Where's the Flux star. This one you may have heard it hit the news over a year ago with some very strange dimmings discovered by the Kepler Space Telescope. Kepler is a space telescope monitoring over 100,000 stars, looking for brief dimmings when planets occult the star to detect these planets. And so Tabby's star, as it's called, had a few very sharp dips. This one was like over 10% of its brightness occulted by whatever object happened here. These are days along here, and this is relative flux detected. Now, previously they had data on short time scales. No one had pieced together to see if there was any generic dimming of the star or brightening of the star. Now people have gone back to try to discover what's going on. So nobody knows what all of these dimmings are. They don't seem to be periodic like planets, maybe pseudo-periodic at best. Some people thought maybe this is evidence of some sort of alien megastructure around this 1 in 100,000 star. It could be dust from, they thought it might be dust from a disk, a dusty disk around the star, occulting the star with planetesimals, perhaps small clumps. You can see over here also very strong dimmings. But the problem with this observation, or with this hypothesis, is that you would expect if there was a big dust disk occulting much of the star, you would also see the heat from this dust in the infrared, in the millimeter waves. And they've gone back with telescopes and looked, and there is no excess heat. There is no warm disk around this star. There is no protoplanetary disk. The stellar physics of this type of star shouldn't be doing this. This is the one star that people can't explain. So astronomers have been studying it. They've now put together a long time scale, and it seems to be continuously dimming, and then it suddenly went deeper. And the scale here, from top to bottom here, is about 4% in terms of its dimming over this time period of observation of Kepler. And they've gone back and looked at this star on photographic plates from 100 years ago, and they believe that there's evidence that the star is dimming by something like 1% a decade up to this point. And then suddenly this happened while Kepler was watching it. So very interesting. Something is happening. Nobody really knows what it is. There is data. You could plot these peaks, and there's something like a 24 to 48 day periodicity, but there's not really enough peaks to confidently say something in orbit is doing this. It could just be a random coincidence.
Al, that sounds fast, 1% a decade.
Yeah. Maybe it's 0.1%. I could be off. I don't have the number right in front of me. So some of the things that have been put forward as potential ideas, and more plot. There's actually an astronomer who's got a blog who's been looking at reviewing all of the things that have been put forward between things in orbit around that star, potentially things in orbit around our star, things in the interstellar medium between us and the star. There are nearby stars that you can look at that are not doing this dimming. It's not an instrumental artifact. They're pretty certain it's actual dimming. One thing it could be is small-scale structure in the interstellar medium, maybe dense, dark objects floating between us and the star, maybe a dim dwarf star with a disk itself, maybe a white dwarf or a black hole between us and that planet with a disk that's slowly moving across. And that we'll have to wait to find out, look at, as they get more data, maybe look at the spectrum of one of these dips, see if the spectrum changes when the dip happens. Maybe it could be an icy object very far out in our solar system, say 10,000 astronomical units. Maybe two comets have collided in our solar system that are chance aligned with this particular star. That's another possibility. Also, no one's ruled out alien megastructures, but they could really be consistent with just about any observation because we don't know what their properties might be. So stay tuned. This is a very interesting thing. There's a lot of astronomers looking at it, hoping to figure out and put together a model that best explains the data. My last news item is something, a mission that I talked to you about a few years back when it was launched, called Gaia. Gaia is the follow-up to the Hipparcos satellite. Hipparcos, as you may recognize the name, is basically was a star mapper, and it put together a huge star catalog. Well, Gaia is going the next step beyond Hipparcos. Gaia's main goal is to create an extraordinarily precise three-dimensional map of more than 1 billion stars, throughout our galaxy and beyond. To do this, Gaia will monitor each of these stars about 70 times over a 5-year period and measure the stellar parallax, which is the tiny apparent looping motion caused by Earth's motion around the sun. So this telescope is close to Earth, and the Earth goes around the sun, and nearby stars appear to move with respect to the background stars. That's called parallax. Well, astronomers presented the first version of the Billion Star Atlas late last year, and it now gives star positions to a precision of a few micro arc seconds for stars down to magnitude 20.7. That's 500,000 times fainter than what the naked eye can see. The data release also contains 3-dimensional data showing the motion of these stars, of 2 million of the stars in our neighborhood, bright enough for Gaia to measure their spectra and determine their speed through the Doppler shift of the light toward away from the Earth. The release also includes measurements of 599 Cepheid stars, 2,595 RR Lyrae stars. These are variable stars vital to calculating the cosmic distance scale, and the positions and magnitudes for 2,152 quasars. So really cool stuff. There's also, if you go to the Gaia website, a cool download that allows users to take the 2 million stars in our solar neighborhood and explore them in 3D. So you can start at Sol and the solar system and move around anywhere in this small area of our local neighborhood. Relatively small, but oh my God, there's a lot of stars there, and it's so hard to find your way back once you leave Sol, because the sun is not all that impressive compared to some of these other stars. And so you actually have to kind of get the constellations to look right and try to find the neighborhood of where you are. It's actually very difficult. I would hate to be a stellar navigator lost in the local neighborhood trying to find my way back. And it really provides a cool sense of scale. Anyways, if you have time, go download it and play around with it. It's pretty cool. So thank you all, and enjoy 2017.
Thank you all. That's impressive. So next up, Gordon, would you like to come present?
Thanks, Kelly. Okay, a couple months ago, you may remember that Tim Cole gave us a little demonstration on a cardboard spectrometer that you could build using a little slice of a DVD. And this sounded interesting. I've always felt it would be fun to play with a spectroscope, and but I'm not quite prepared to spend $1,500 or something just for something that I may or may not find all that interesting when I play with it. So I downloaded the template for this cardboard spectroscope, and I cut out a DVD and washed it out and split it up the way it was described. And I happened to be in the dollar store, and I found a $3 USB video camera. So I bought that and hooked the two up. And I started playing. This was back in the fall, so it's still warm outside. So the first thing I tried was inside, and I got an LED light. Guess you're expecting me to do this, right? Center button? Right, up, right button, okay. So that's it, and these are mostly done, the indoor ones are done reflected off of a white paper. So this was one LED light that I tried. Now I went outside and I tried it on my blue car. So that's a reflection off the blue car. I then tried my SUV, Burgundy. And you can see there are differences. Okay. Then I tried the sky. This one was reflected off white paper. A piece of brown cardboard in the shade. My lawn, which this year happened to be green. I tried an LED flashlight. Again, that's reflected. And this one was a halogen lamp And I think that was pointed directly at the halogen lamp, but I may be misremembering it. Anyway, you can see there are quite a few differences. Okay, the LED flashlight and the halogen, quite different. I did try it on a star, but it obviously wasn't bright enough, and I didn't have time to fiddle. I was still trying to hold the camera against the little cardboard tube. So what I'm going to do is I'm going to rig up some way of actually mounting that and then mount it to an eyepiece, and I'll get back to you. Thank you.
Okay, we're having some technical issues. I might stall a little bit. So we're gonna go straight to observation reports. So we're gonna do kind of half and half if we can. Number one. All right, are you guys are you ready to present your observations? Well, Rick, there you go.
Here comes Roman Skyping in.
Roman? No, I'll be doing his presentation. He's not a mystery member anymore. Everyone's gonna guess it.
Good evening. So, how many people went out to see in November, on the 14th-ish? Went out to see, it's dark in here, went out to see the supermoon. All right, yeah. Let's go to my first picture, or maybe I can do that. Right button. Oh, there we go. The moon. Isn't that magnificent? Supermoon. It's so close and it's so big. Wow. I happened to be out observing all night that night anyway, so I went out and I watched it. And to be honest, it was a spectacular full moon. I mean, it was so bright and the moon was huge. Oh, was it any huger than normal or brighter than normal? I don't know. Knowing in advance that it should be, yeah, it felt like it was, but whatever. It was wonderful anyway. So I really enjoyed it. So what is a supermoon? Well, a supermoon basically, when we have a full moon, it can occur any place in the moon's orbit. If it happens to occur when the moon is at its closest to the Earth, we have a supermoon. If it happens when the moon is at its furthest point in its orbit, the trending term now seems to be a mini-moon. So sort of next spring, early summer, we'll be getting mini-moons. The moon will actually appear about 14% smaller. Okay, 14%, that's quite a bit. I'm sure many of you have seen the photographs where they have the comparison. You know, the two halves are done, you know, at supermoon and mini-moon. And it's obvious, but can you look up in the sky and then 6 months later look up and say, oh yeah, that's 14, maybe 13% smaller? I don't think I could do that. So the other thing that's of interest, and the reason why this was kind of exciting in the fall, is because not only is the moon's orbit elliptical, but it actually squashes and lengthens and squeezes and oscillates. And it just happens that in the fall, the perigees were generally closer than they normally are. So for instance, well, part of the problem, of course, is does the full moon occur at perigee or close to perigee? So in October and December, the full moon wasn't right at perigee. So the moon was a little further away, a few hundred kilometers, maybe I think 800 or something. So the other thing is, let me see, what have I got here? Okay, so those two were about 1% further away than the November one. because of the changes in shape in the orbit, if we want to find one that's closer than the November full moon, we have to go all the way back to 1948, when there was one that was 29 kilometers closer. Now remember, the moon is like 350,000 kilometers away. So 1948, there was a supermoon that was 29 kilometers closer. And if you wait until 2034, there would be one that's 71 kilometers closer. Ooh, yeah. So the important thing is that we had to get out and see this one because it's been a long time since the last one's a long time since the next one. Now, how many people actually went out the evening before? Because perigee and full moon were actually almost at sunrise on the 15th. So how many went out the evening before or the evening after? If you did, you saw the overture or you saw the curtain calls, you completely missed the opera. Because it turns out in the evenings before and after, the moon was actually already 750 kilometers further away than perigee. That's upsetting. So I'm glad I was out. I'm glad I was out checking it out all night long. So, if we go to the next slide, we find out something even more interesting. Yeah, we have a laser. Okay, so in this diagram I made here, this is the Earth, here's the moon. I'm looking down on the northern poles of both of them. The two disks are about approximately proper scale, but the moon should be over here about 20 times as far away. And I'm not quite as tall as that. So here's me watching the moon. This would actually be, given the direction, I think this would be watching the setting moon off the horizon. And here's me looking at it when the moon is at the meridian, assuming I was on the equator. You can see that up here,
It's only a step away.
I'm 6,400 kilometers closer to the moon than when you're watching it rise or set. So if you were watching it at sunrise, at moonset, you're actually 6,400 kilometers away, plus the 750 kilometers that the moon has already moved away from perigee. So that's like hopeless. If you really had to be out sometime around midnight if you wanted to really see it at its biggest. And I was lucky that I was out observing, so I was out checking it out every half hour or so. And I must admit I couldn't see any difference. However, all this thinking about this stuff did make me wonder. So this 6,400 kilometer difference out of 360,000 kilometers, could we actually measure that? So what I did was I only thought of this sort of about 9 o'clock in the evening, so I grabbed my camera and a 300 millimeter lens, and I ran out, and I took a few shots of the moon, and then I went out about midnight, took some more shots, and then I went out as the moon was setting, took some more shots, and then measured them. It took them all at the same focal length, same settings and stuff. Unfortunately, the ones at moonset came out blurry, so they weren't very useful. But the other two sets came out fairly good. So if we can go back, there we go. So that was when the moon was on the meridian, and that's when it was rising. Did you notice it? Yeah? Okay. Well, so what in fact, I did, so well, actually, if we go back and forth here, I want to go back. There we go. Oh, see? So it does go back. Another interesting thing you'll notice is it does look like the moon rotates a little bit. That's actually parallax, because not only have we moved closer, but of course we've moved sideways in its orbit, and it's moved sideways in its orbit a bit. So we do have a very slightly different perspective. But if we take the two pictures and overlay them, you can see at the top and the bottom, there is a slight difference. So now this works out. I measured this. I should have used a longer focal length to get bigger scale and stuff, be able to measure it more accurately. But this is what I could do with sort of 5 minutes notice. I measured the close picture as being about 0.8% larger than the farther one. But if you calculate the distance, the 6,400 kilometers, it should have been closer to 2%. So why am I only getting 0.8? Well, of course, we aren't on the equator. So up here at 45 degrees north, our distance from the Earth's axis is only about 70% as far. So that reduces the difference in size. I also shot the first images slightly after moonrise, a couple of hours in fact. And you got to realize, as the Earth spins around, even at 45 north, we're approaching the moon at about 1,000 kilometers an hour. So if you shoot the moon 2 hours after moonrise, you know, you've already lost a couple of 1,000 kilometers. And also, the moon and the Earth's equator were not aligned, so our motion towards and away from the moon is somewhat reduced by the cosine of the angle, etc. So what it worked out to is, when I did all the math, the one image should have been about 0.9% larger than the other. So I figure with 0.8%, I got pretty close, given that I'm only talking about 600 or 700 pixels total height.
So Rick, you didn't think atmospheric refraction plays into this?
No. No, it shouldn't. In fact, actually what I did was I used the images in such an orientation that the refraction would be minimized. So it shouldn't have an effect. At least not a large one. All right? So, 2 weeks after that, this is my other observation from the fall. Last year I completed the Williamson Lunar Observing Certificate, which is a list of several hundred objects to see on the moon, different events and stuff. There's still about 15 of the challenge objects that I haven't actually completed. They're not required to get the certificate. And one of them is seeing the moon when it's less than 24 hours from new. So on November 28th, 2 weeks after the supermoon, it was new moon, and I got up in the morning and I bleared out the window, and it was mostly cloudy, but I noticed it was light along the eastern horizon, so I headed out, and sure enough,
Point out to us where it is?
Pardon? Well, when we get there. I haven't found it yet. We're still looking. So I got out, and I spent about 15 or 20 minutes and did finally find it. Very thin crescent. It's amazing how thin this crescent is. And I followed it for about half an hour. One more shot, you can see it up there. You can see the sky is getting bluer and stuff. You can also see that it's getting cloudier. And as it happened, about 5 minutes after this picture, the cloud deck came in and the moon was gone. And when I checked the books in the house later in the day, it turns out this picture was taken when the moon was about 24 hours and 20 minutes old. So I missed by 20 minutes. So I am continuing to try and find a moon less than 24 hours old. So thank you.
It's going to be a hard act to follow. Okay, back in November, this is my report that I was going to give in November, but then I got sick and didn't make it. It was a dark night. There we go. Okay, so I was out, to my great surprise, from my backyard in Orleans, which everybody knows by now is very light polluted, I was actually able to find M33. And I think that's probably only I think that's the first time I've actually seen M33 from Orleans. What was really interesting was my 12-inch Dobbs a go-to, and this night it was acting more like a go near. So I had punched in M33, and when it stopped moving, there was this little fuzzy thing close to a star, and I looked at it and I knew that wasn't M33. So I figured, okay, well, it's off a little. I started fiddling, and just a little to the left was M33. So I started wondering what was it that I was seeing, and a little research showed me that it's actually, NGC 604. So, whoop, sorry. Laser pointers in the center, or the top one? Top one. There we go. Okay, so that's M33, and over here is NGC 604, which is apparently magnitude 14. It's a hydrogen 2 region that's 40. If it were where the the Orion Nebula is, it would be 40 times the size. That's how big it is. That was kind of neat. I was quite excited by that one. And the next one I have is Mirac's Ghost and NGC 404. It's 11th magnitude galaxy. It's about 10 million light years away in Andromeda. And it's a dwarf lenticular galaxy. It's just 7 arc minutes from Mirac. And it makes it, because of its proximity to the star up here, whoa, back. I was doing this all day on email too. I kept sending them instead of hitting attachment. So there's the star, and it's 7 arc minutes to the ghost. And then there should be one more, I hope. No, you don't? You didn't get my photograph? Oh dear. I had this wonderful photograph of the conjunction earlier in the week of Venus and the moon. Now, what was really interesting and unusual about this conjunction is it was actually visible. There were no clouds. Thank you.
All right, so I'm going to step in for Roman tonight. I took some notes. I don't actually know what he sent us.
He's watching.
Okay, so this picture was taken by Roman, obviously, in Iqaluit. And what it is the sun during the winter solstice, so on December 21st. This picture was taken at 11:43 a.m. So how he described it is this is the lowest, highest point of the year. So the sun didn't get any higher than that day. And so what he meant to say, the sun is about 3 degrees above the horizon. And after that point, it just set right back down. Okay, thanks. Janet? Janet?
Happy New Year, everybody. I was out for a walk with my spouse Brad on New Year's Day around 5:15, and I had actually been taking pictures of the Ottawa River with my cell phone, and so on the way back to the truck, I happened to notice Venus and the crescent moon, a nice conjunction. And so the image that you see there is near the Ottawa River, and I took it with my cell phone, so not too bad for a cell phone. Next, please. Right. This is my ode to Leonard Cohen instead of Bird on a Wire. We've got the crescent moon on a wire, and I noticed that there's actually wires up here as well, so the whole thing is very confusing. Anyway, a little bit of a close-up with the cell phone. So, you know, if taking photographs with a cell phone of the night sky makes me an astrophotographer, then I'll happily accept the appellation. Thank you.
All right, so like I said, we have a lot of observations, so we're going to show the rest of them in the second half. So for now, we're just going to go and take a break. We've got time today, take 15 minutes. And during the break, the calendars are still on sale, $16 for one, $30 for two. So they'll be available at the table just over there. Okay, so I think we owe Gordon a bit of an apology. So we found his picture. We're going to let him present it real quick. It's all yours.
Kelly,
Yeah?
first observation.
Yeah, that's what I thought. It's the first
Yeah,
observation.
first observation, yeah.
But we're
Simon,
after sign.
not now.
Oh, after Simon? Oh, good, okay.
There you go. First meeting, right? In that case, are you guys ready for Simon? Yes. Are you really, though? Yeah. All right, welcome, Simon Hanmer.
All righty. You're quite the crowd. You are. Can we have a light so I can actually...
Podium, please, and turn down the house lights.
Yeah. Because maybe if you sort of put some lights on me, I can actually see my notes, which would help. Not seeing much. It's getting better. I can see that there are words here. All right, let's see what we can do.
Go into the light.
Yeah, exactly. Yeah, I know. All righty. So, now Al Scott told you that he just presented the news. So I'm going to present the weather forecast. All right. Now, if you remember, my last two talks from this podium addressed the supposed scientific consensus regarding the origins and subsequent evolution of our moon, including the significance of its impact history for our understanding of the solar system as a whole. Now, as we saw during those two talks, scientific consensus turns out to be far more fragile than the popular media realize when they blithely report that scientists have proven that whatever, A, B, C, D. However, astronomically speaking, the moon is not alone in this regard. So let's stay within our solar system and let's take a look at, whoops, that was me. Let's take a look at Mars. No, that was my notes. Now, for God's sake, don't get me into a fit of the giggles, because I won't stop. All right. Now, given all the time and money that's been poured into going to Mars since the early 1970s, I mean, remember, we've been doing this for a long time, you might think that some sort of scientific consensus regarding its history would have started to appear by now. Now, it's true. We really do have a good idea of what its surface looks like, and we can even distort it with 3D and vertical exaggeration. And we can make very detailed digital elevation models, in other words, maps of its topography, that everybody can agree upon, some form of consensus, if you like. So here's the geography of Mars, and for our purposes, I want you to bear in mind that all this red and yellow stuff here, this is what's known as the Southern Highlands, and I'm going to be mentioning these a number of times. And this up here in the blue is the Northern Lowlands. So clearly blue is low and red and yellow are high. And this area here, Arabia Terra, is going to be important later in the talk. So, there we go. And We even have a pretty good idea of what the Martian surface looks like at ground level. But there are two fundamental questions that are currently driving our scientific activity regarding the red planet. And these are, was there ever standing water on its surface? And did it last long enough for life to develop there? Now, these four artists' impressions of what a warm, wet Mars might have looked like prior to about 3.5 billion years ago, which is referred to as the Noachian epoch. And I'll use that word a number of times. If I say Noachian, I mean old, older than 3.5 billion. These are symptomatic of what a part of the planetary scientific community perceives regarding standing water on early Mars. Note how the northern ocean in each one of them is represented here in blue. And now this implies liquid water around the North Pole. And that implies a warm climate with a hydrological cycle of rainfall, rivers and streams, lakes and deltas, all accompanied by clouds. A warm and wet early Mars is a perfectly valid hypothesis. It's supported by highly reputable scientists, and it's well worth taking seriously. But over time, it has come to be seen as the favored model, bordering on a consensus, at least until very recently. For the past 18 months, there's been a mounting open debate regarding the early climate of Mars, during the course of which many planetary scientists of good international standing and reputation are promoting an alternative view. Instead of a warm and wet Mars, what if the early Martian climate was in fact cold and dry? Now, this evolving debate is still ongoing, and it remains unresolved. But it's now maturing to the point where we as amateur astronomers can follow the reasoning on both sides of the discussion and thereby participate, even if only as observers. So I thought it would be a good idea for us to take some time to look at this debate tonight. Now, let's start by reminding ourselves of what the warm and wet model, which has held sway for so long, is actually based on. And it's based on channels, lakes, and deltas, some of which I've already talked to you about in the recent past. The channels come in all kinds of sizes, and some of them can even be seen at the scale of the planet. There's one obvious channel, right, the Martian Valley. But there's also huge ones here. This one here is Casei Vallis. It's 2,000 kilometers long. But there are many others down through here that you can see as well. They're not all focused here. There are others over here, which I'll actually talk about. Actually here or here, depending on your preference. I'll be referring to a place called Mardim Vallis, which is another one of these channels. There's also a purported ocean, which pretty much coincides with these northern lowlands. Now, the lakes, which I mentioned, they're a little too subtle to see here, but we'll actually see them in just a moment. Now, I'm hoping that I press the right button and get the effect that I want. I did. Good. Okay. So meanwhile, let's take a look at the north end of Casei Vallis, north of the Mariner Valley. Mariner Valley, Casei Vallis, and we'll look at this. Now, Casei Vallis is the largest outflow channel on Mars, and it's huge. As I said, it's 2,000 kilometers long, and this distance here from one side of the valley to the next is in the, well, there's the 100-kilometer scale bar, so you can see it several hundred kilometers across. I put this image in tonight because it serves to remind us of the kind of direct observational evidence that exists all over Mars for the erosive power of surface water on the planet. So note, for example, the multiple channels, this one here and this one here, which then branches, which are actually cutting into the floor of the main channel itself. And then, in particular, note the erosional remnant islands. These things out here with what's the word I'm looking for? With the flow geometry, if you like. This is where water flowed around, eroding these islands and leaving these as high-standing remnants. And both of these are similar to features that can be seen all over the planet. However, Cassae Vallis is supposed to be the product of catastrophic, near-instantaneous erosion by floodwaters, and I've talked to you about this when I came back from my 14,000 kilometer trip to Washington State when I went to Mars, in inverted commas. So while this valley clearly says surface water, it is not interpreted in terms of long-term surface water indicative of a warm and wet climate. So what exactly does constitute evidence for long-term surface water? Lakes. Now, this is a false color image, the blue. There is no water in these depressions, not anymore. But they've used false color blue to highlight the idea that this is a color image of the Eridania Lake system. And it's located in the Southern Highlands, that I've mentioned to you on the previous slide, several slides back, just south of Gusev Crater, and that's up here. Gusev Crater, of course, is where NASA's Spirit rover landed. Now, originally, this was the largest lake on Mars because it was all, in fact, one body, about a million square kilometers in size. And it then shrank to a system of smaller interconnected lakes that you see here, that linked to the lake in Gusev Crater via an outflow channel known as Mardin Vallis, and that's this thing here. And again, note the scale bar, 500 kilometers here. These are pretty big features. Now, this lake system is relatively easy to identify from the flat lake beds that were left behind when the water eventually disappeared. But other evidence for ancient lake beds on Mars is more equivocal. Let's take a look at that. Now, here's an example. These three images are all interpreted as the dried up lake bottom sediments that cracked into polygonal shapes as the sediments dried out. The one on the left here, that's a textbook image from a known lake bed here on Earth. But note the scale bar. That's 5 centimeters. The next two images are from a dry lake bed in California, that's this one here from Coyote Creek, and from a purported lake bed here in Mars. Now, the polygons here are way bigger than in the first example. That's 150 meters. That's 500 meters, compared with 5 centimeters. But between the two images, here and here, the sizes are comparable. All very well, but a different scientific team interpreted the same Martian example, that is the same example, in fact, as what I just previously showed you, as the products of permafrost, the kind of thing we see in northern Canada. Hardly a ringing endorsement of the lake bed interpretation. You know, maybe these two teams should talk to each other more. So what about river systems? Well, here's a typical river system from Earth. It shows tributaries converging and linking into larger channels that themselves link into the main channel. So there are the larger channels and the small tributaries all linking in a typical geometry. The scale here is on the order of well over 100 kilometers. And this is the important thing. Establishing such an integrated fluvial system requires thousands of years, at least, thereby representing direct observational evidence for medium to possibly long-term surface water, even though it could be seasonal rather than uninterrupted flow. Now, this image is from Mars. Note there's the scale bar down there, 20 kilometers. And it has all the hallmarks of the terrestrial river system that we've just looked at. Various small channels converging into a larger channel, there they go again, and eventually converging into the main channel down here. This smaller image here is simply a slightly larger field of view with respect to this image here. Noachian, in other words, older than 3.5 billion years old. Noachian examples of this kind of feature from early Mars history occur in many places throughout the Southern Highlands. As I've shown you in a previous talk, in fact, it was a talk you gave me an award for, where rivers empty into lakes, they slow down. And in slowing down, they dump the sediments they were transporting and they form deltas. Here's a delta. And the edge of this delta is visible across the top of the slide here. There's the edge. And you can readily see that the river channel, which is coming down like this, it branches into multiple channels as you flow downstream towards what would have been the lake. And that lake would, of course, be formed by standing water, standing surface water. Now, this is prima facie direct observational evidence for medium to long-term standing surface water. And again, Noachian examples of deltas from the early Mars history occur in many places throughout the Southern Highlands. Well, so much for channels, lakes, rivers, and deltas, all of which require a certain amount of time to form and to mature. But the key witness to a truly long-term, globally wet planet would be the existence of an ocean whose time frame would be in the order of hundreds of millions of years. I've even read that they're talking in terms of maybe up to 1 billion years. Now, let me say at the outset, the existence of this northern ocean, which would be represented here in the blue, is controversial to this day. Whatever, let's briefly look at some of the observational evidence for a shoreline at the boundary between the Southern Highlands, which is in grey, and the northern lowlands in the shades of blue. Now, the bright colours that you see in here, the yellows and the reds, these represent the distribution of approximately 40,000 north-flowing channels in the Southern Highlands, some of which have deltas at their northern ends, all marking the southern shoreline of the proposed ocean, which would be here, except through here. And that's because the boundary between ocean and highlands has been distorted. It's been distorted by the tectonic evolution, the rise, getting excited, the rise of what's called here the Tharsis uplift or the Tharsis plateau. So that can easily explain why our shoreline is sort of pulling away from where we might otherwise think it should be. Now, a very recent study published in 2016, I mean recent, interpreted the images shown here as fields of giant boulders at the top here. Can you see this yellow line there and that yellow line there? That's 10-meter scale bars. So these things here are boulders the size of houses. And large-scale channels in the lower image here, these things here, these large-scale channels, this 4 kilometers. So the channels are in the order of 10, 15 kilometers long, and they're in the orders of hundreds of meters across. And these are interpreted as being, they're located at the southern edge of the proposed ocean, and they're interpreted as being created by an incoming tidal wave and the outgoing backwash of a tsunami. And this tsunami would have been the result of a major meteor impact into the proposed ocean at about 3.5 billion years ago. Finally, here's some high-tech evidence for our northern ocean. This is a map of the Martian North Pole, which would be about there, showing data from ground-penetrating radar from the European Space Agency's Mars Express orbiter. Now, real dielectric constant. For those who like to know these things, I had to look it up. The dielectric constant refers to the ability of a material to concentrate or store an electric flux or electrical energy. For the rest of us, it's enough to know that the low values of this dielectric constant, which are represented by the pale blue color here, are best interpreted as indicating the presence of fine-grained sediment. And that is the kind of material you would expect to find accumulating on the floor of a large body of standing water, such as an ocean. So, okay, we've got clear observational evidence for water on the surface of early Mars, including river systems, lakes and deltas. And pretty good, although controversial, observational evidence for the likely existence of an ancient ocean. So what's the problem? Why is the favored warm and wet model bordering on scientific consensus being questioned today? And that's what I want to look at now. Fundamentally, the problem is this. Given the distance of Mars from the Sun, it receives about 45% less sunlight than we do here on Earth. In addition, all of the models of solar evolution, actually stellar evolution, remember our Sun is a star, proposed that the early Sun was 25% fainter than it is today. So you put all this together, and Mars was inherently a cold place during the Noachian. In other words, prior to about 3.5 billion years ago. But this is not in itself the problem. The problem is that computer-based climate models for early Mars, based on terrestrial climate models, failed to predict a greenhouse effect capable of generating a warm, wet climate. Now, there are several variations on this general theme using various mixtures of carbon dioxide, water, hydrogen gas, usually combined with sulfur. Think stink bombs, if you will. For those of you that are old enough to remember what a stink bomb is, I see all the men smiling. They also incorporate dust in these models, they incorporate aerosols in these models, they incorporate clouds in these models. These are very serious models at various atmospheric temperatures, pressures. But all either fail or they require very special conditions, which between us is otherwise known as special pleading. Now, this has led some planetary scientists to suggest that perhaps the climate of early Mars was in fact not warm and wet, but cold and dry, but punctuated episodically through time by warmer conditions that lasted just long enough for the erosional and depositional landforms, in other words, rivers, lakes, and deltas that we've just looked at, to form. Now, some have suggested that the heat derived from large meteor impacts into a cold, dry Mars would generate a temporary steam atmosphere. In other words, a hydrological cycle from steam. Others have invoked outbursts of voluminous volcanism to temporarily boost the atmospheric greenhouse effect of a cold, dry Mars, and thereby a short-term hydrological cycle of rain, runoff, erosion, and deposition. But episodic wet conditions pose a problem, and it's very simple. Water flows downhill. Once you've melted your upslope sources for water from one episode, however you actually achieve this melting, doesn't matter. How do you then recharge that uphill source region with more water in preparation for the next melting cycle? This image here clearly shows that since the channels and valleys, that's these bright colors here, remember, are mostly found in the northern parts of the southern highlands, then that's where the source region recharge needs to occur. And this is where we now enter the complex realm of climate modeling. But you know me, I'll keep this as simple as possible. Now, please note, we're going to have to ignore the Northern Ocean for a few minutes. Everybody else that's actually doing this climate modeling does this, but I will come back to it at the end. Now, since 2012, I need to go there. Since 2012, a group of planetary scientists of excellent reputation have been publishing a series of papers where they specifically address this question of recharging the upslope water sources under a cold and dry climate on early Mars. If you've got a dry climate, how do you get water up on the top of mountains? As you can see here, they started by predicting various aspects of global temperature distribution. That's what these various colors represent. There's a color scale there going up to, it's in Kelvin, by the way. So zero centigrade is about here somewhere. Don't worry, we're not going to be looking at this in any detail. I just want you to know that they've done this. And they started predicting this global temperature distribution for different densities of the atmosphere. There's one atmosphere. What they mean by one atmosphere is atmospheric pressure at the surface of the planet, which is the equivalent of our average atmosphere on the surface of the Earth. So it's easy. You don't have to worry about bars and millibars or what have you. And then this is very low atmospheric pressure. That's actually pretty much modern Martian atmospheric pressure, and then there's an intermediate value there. And they simply say, look, this is annual mean temperature, daily averaged annual maximum. Don't worry about it. I just wanted you to see that they've actually analyzed this. There we go. Then they apply these temperature models that they've derived to simulate. Remember, this is what computer models do. They simulate the development of surface water ice over the planetary surface through a time frame. And that time frame lasts for about 40 average Martian years. Remember that a Martian year is about 2 Earth years, so approximately a century. And what they've done is they said, look, going down this way, this is 1 orbit, 0 orbits, 4 orbits, 20 orbits, 40 orbits, each orbit being 2 Earth years. So this is time going this way. And they've got various conditions here, which I'll explain to you in a minute. Now, what they've done here is they've modeled 2 very thin carbon dioxide rich atmospheres plus water vapor on a planet with the same inclination, you know, the inclination of the rotation axis of the planet with respect to the orbit that it's going around the sun on. They've used the same inclination as Mars has today. We're not going to spend much time on this one here, by the way, because you can see nothing much actually happened. They got a lot of ice up in the north, a little bit of ice started forming down in the south, but it was really very, very slow. And this is a very slow transfer by sublimation of some water ice from the north towards the south, with a minor ice buildup in the northern parts of the southern uplands. In other words, their conclusion is that low pressure atmospheres, these really low pressure atmospheres here, that's today, and that's just a little bit less, they really don't produce the required results. So we're not going to spend any time on that. Move on. In this example, they started changing they changed the starting configuration for this simulation here. In this one, they actually put ice into what we would call the northern lowlands today. But in this one, they artificially said, no, we're going to put all the ice at the North Pole and the South Pole, and we'll see what happens. They also, having learnt from their previous simulation, jacked up the CO2-rich atmospheric pressure to the equivalent of our atmospheric pressure here on Earth. This is more interesting. They're actually getting more change. You notice the significant transfer of ice from here or from here. As you get down through time, you get lots of ice transferred down into the south here. In fact, into the southern highlands. But they're still maintaining a cold, dry climate, which is good. Now, notice one key thing here, and that is that the overall starting configuration doesn't have much effect on the result. It doesn't matter if you start with the ice all in the polar regions or all up in the northern lowlands, the end result is very, very similar. Okay. And then in this last example of one of their simulations, they really went to town. They started with the ice at the poles, in all cases here. The ice is at the poles. And then they tipped the planet over from about a 25-degree obliquity, where it is today, to about 40 degrees. They get away with that because Mars, actually, its obliquity precesses chaotically. And it is quite common for it actually to lie at about 70 degrees to its orbital plane. And that can happen in the space of literally within a time frame of about 100,000 years. So they went for 45 degrees, and they also messed around with the topography. In this example, they left Tharsis in place, and in this example, they got rid of it. Artificially, of course. So what did they get? They got what they were looking for. Major water ice buildup from the poles, certainly the North Pole, in the northern part of the southern uplands. And you notice that the presence or absence of the Tharsis rise not present here, but it is present there, did have an effect on ice distribution, but not on the overall result. This patch of ice here, where Tharsis exists, is not present where it doesn't exist. That makes sense. Tharsis is highland. It's upland. So no upland, no ice. But they're getting their ice buildup exactly where they want it, in the northern part of the southern uplands and in Arabia Terra. I'll come back to that in just a moment.
Simon,
Yes.
The tilt of the axis change because the planet doesn't have a large moon like ours?
Exactly. Yes, I've been through this one with you before when I discussed the role of the moon. Our moon, compared with the size of our planet, is huge. It's about the size of Jupiter's moons, but look at the size of Jupiter. And it's that which stabilizes the precession of our own orbital axis. Otherwise, we too would have these wild variations in climate such as Mars has had. So, there we go. So how did planetary scientists interpret their results? Without a moon, such as Earth's, Mars precesses chaotically. As I say, it can actually, its axis can tilt over to easily 70 degrees. At high obliquity means that the axis is tilted right over. At high obliquities, the poles of the planet are anomalously warm because they actually point more towards the sun. While the sub-equatorial highlands are anomalously cold. So water ice sublimates at the poles and migrates equatorially. A good part of this, what they call the icy highlands effect, is due to something called adiabatic cooling, which is a fancy phrase that simply means that a gas cools as it expands. This is why you have a compressor in your fridge. That thing making all the noise, it's compressing a gas, and when that gas decompresses, your fridge gets cooler. And it's also why clouds form over high ground. When atmospheric gases rise on Mars, they decompress and cool. And then they precipitate snow over the southern highlands because that's what atmospheric gases do when they rise over mountains. Now, as an interesting twist to the story, one of the reasons this particular climate model was developed in the first place was because warm and wet climate models predict lots of precipitation here in Arabia Terra. And at the time that this model was put together, which is quite recently, there were very few sightings of channels there. So people said, well, hey, if you're supposed to have a lot of rain here due to the warm-wet model, and if you don't actually have any erosional channels, then there's something wrong with the warm-wet hypothesis. The cold and dry model correctly predicted and corrected that. Well, guess what? No, I got that the wrong way around. The warm-wet model predicted there would be a lot of rain in Arabia Terra. And there were no channels to show that there had actually been that water. This is better. And the cold-dry model corrected this by showing that right in Arabia Terra, you didn't actually get that much rain. And this is where the guess what occurs. In 2016, another group of scientists took another look and found all sorts of evidence for abundant rivers and streams and even lakes in Arabia Terra, leading some other scientists to claim that this provided support for a wet and warm model and that it put paid to the cold and dry model for early Mars. You can see the channels they're talking about. There's a channel there. And see how it splits and then joins again, splits and then joins again? I'm told by those that work on this, this is absolutely typical of what you would get with erosion due to running water. And here is an example of a meandering channel, which actually then empties into, or comes out of, I'm not sure which way it flows, a lake. And this is from Arabia Terra. So as I said, the debate continues. But let's just stop and think for a minute here. What about that purported Northern Ocean, which I ignored temporarily and that I will come back to at the end, which is what I'm doing now? As I said, its existence is controversial. It's even highly controversial. But if it existed, it had to be liquid water. The deltas and the tsunamis tell us this. And it would have supported a global hydrological cycle. So now ask yourselves, what exactly is this debate about? This debate about a warm, wet early climate or a cold, dry early climate. From my perspective, it pits direct observational evidence against computer models of climate development. No one's challenging the existence of the Noachian river systems, lakes, and deltas. The Northern Ocean and its shoreline are indeed contentious, but constitute a serious hypothesis. But it would be very difficult for climate modelers to call their computer models into question, since they are essentially the same as those that play a central role in climate science here on Earth, and all that that implies both scientifically and politically. Now, I always like to leave you with a take-home message, and tonight's message is this. Martian climate science is indeed challenging the warm and wet model for the climate of early Mars. While it cannot easily simulate the warm and wet climate model, it seems to successfully simulate some aspects of the cold and dry climate model. However, neither model has the upper hand in this ongoing debate. And I would suggest that the potentially most fruitful avenue of endeavor to help decide between these competing computer-based climate scenarios would be to reinvest in further direct observational research to resolve the question, was there or was there not a long-term liquid Noachian ocean on Mars prior to 3.5 billion years ago? If it existed, it requires a warm, wet global climate, whatever the computers say. As always, thanks for listening.
Thank you, Simon. That was great. Okay, so we're gonna head right back to observations. I think we owe Gordon a really big apology. So Gordon, it's all yours.
Thank you, Kelly. So here's the photograph that we found during the break. And we got Venus in the top left and the crescent moon. Very much the same image that Janet showed. I think, Janet, you said yours was about 5:15.
About 5:15.
Yeah, and this was at about 10 to 5. So there we go. Thank you.
I started teaching an online class for Loyalist College in Belleville. And one of the things Loyalist requires is individual study programs for each modules for each student. One of my students, a former Air Force navigator, decided he wanted to do his on Polaris and its impact on navigation. And he decided to include this photograph of Polaris and, as he put it, Polaris and Friends, as part of his report. Why I thought I'd ask him if he could bring this in is this is the first astrophoto he ever tried taking. And he did it in one evening through, as he described it, considerable trial and error, and discovering that he couldn't do a long exposure with his camera. So what he's done here is discovered astrostacks and discovered how to take multiple images, align them, and stack them. And as he points out, the red blur is an airplane, which tells you it's a genuine, authentic astrophoto. Anyway, I thought it was a great effort for somebody's first effort, considering that the course did not include any kind of astrophotography, which is good because I was teaching it and I suck at it. But I think it's really nice to see what people are willing to do just on their own hook, and I toss that out as something for our regular members, which is give it a shot and bring it in and show us what you can do. Because, okay, I mean, you know, we all see marvelous work done by fantastic astrophotographers that we have here, but they started somewhere. And anyway, I thought it was a nice thing to show you guys, and a shout out to a very capable student. Thank you all.
Hey everyone. So this is my image of the Rosette Nebula. So I took this one actually almost a year ago, March 11th, 2016, from actually Paul Cloninger's place. Rosette Nebula is a large spherical H2 region in the constellation Monoceros. It's about 5,000 light years away, and it's 50 light years in diameter. So it's also known as Caldwell 49 or NGC 2237. So this was shot with my Canon 60DA through a Skywatcher Equinox 80 ED. 1600 ISO, and it's about 2 hours worth of exposure. All right.
Happy New Year, everyone.
Happy New Year.
This past summer, I decided to go up to the Algonquin Radio Observatory. Where's the pointer here? So I took this picture at the Radio Observatory of the Milky Way, and as you can see here, we've got Mars here and Saturn. And I was looking at it this afternoon again, and I noticed that M7 was right here. But what was kind of neat about this picture, I took a tour at the observatory, and the guy who runs the place up there was saying how he spends a lot of his time mapping out the exact positions of satellites. That's one of the major functions of the radio observatory. I don't know if this is going to show up on the video cast here, but this post right here is a GPS post that, as he was saying,
Point
it's.
at it again?
Sorry?
Point at it again?
Just right in the corner there.
Okay.
It's kind of hard to make out. It's not. I guess it's not the same shape as the bushes around. But in any case, apparently the way the satellite model is going for, or the GPS model is going for communications for position, is a ground-based model, because eventually, as he was explaining, right now, essentially one nation is in control of one constellation of satellites, and that's changing. There are new constellations of satellites coming up. But what happens if something like that goes down? So, and suddenly you can't have, GPS positioning based on those satellites. So this post down there is a new means of being able to determine your position relative to that post. And he was saying that post is about the most accurately known position in the entire solar system, accurate to about 1 millimeter. Here's the radio radio observatory again, or well, not again. My next shot is also of the radio observatory, but this shot right here, I wasn't originally going to show this one, and I kind of thought that if you look at the previous picture again, this is after a lot of processing, so that you can really see the details in the Milky Way. It really makes the contrast and the colors pop out. Whereas this one, I didn't do too much processing on it, the way that I would have done it for the previous one. This one right here, I processed it to look more like what it actually looks like when you're out there. And the thing that, like, they're both from the same night, and then of course the clouds rolled in later. But what struck me about this one really was just that out of the radio observatory, it's so dark out there. When the clouds roll in, you don't see light polluted orange clouds rolling in. You see dark patches in the sky. So I kind of thought that it struck me as interesting. Here's the radio observatory again. So this one I have a time lapse I've got to show you, and I did it on my time lapse slider, so that the camera moved a total of about 2 meters from start to end horizontally. And it's just enough that the dish will actually rotate throughout the time lapse. So I'll have to show you that maybe next month. Yeah, sorry. Suspense, come on here. This next one here, I took this in I guess mid-July when we had I don't know, Rick, was this a supermoon? Anyways, I I grabbed my bike and I went down south of Manotick on what used to be train track. That's now an all-purpose trail. And I used an app to let me know exactly where the moon was going to rise. And I sat there waiting for the moon to rise, and as it rose, it just went click, 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 kind of thing. And you know, I mean, the distance between, this is a telephoto lens, so the time it took for the moon to break the surface of the horizon and get to where it was maybe about 30 seconds. And in the process of capturing this one, I took, I think it was something like 7 pictures, start to end, of varying exposure so that I could put it together in a high contrast image afterwards. What struck me about this, I knew the moon was going to rise and it was going to be full that night, but I didn't expect the color of the sky to be so purple. Or the telephone lines. Actually, there are telephone lines there. And I thought I'd show another shot of auroras tonight, as of my usual shot, or my usual place up in the Highlands. This one will also be another one that the raw data is still sitting on my computer, but I'm going to turn this into a time lapse, another 1,500 images or so. And Paul Cloninger and I were up there that night. I think actually Andrew Brown and Terrace was up there as well too. And so the 4 of us were imaging up there together. I decided to put a little light on a post that was up there and shine it on the grass. Do a little bit of light painting. In any case, so I'll show you the time lapse when I have it ready. And that's all I have for tonight.
Well, hi there, everybody. Hope you all had a nice holiday. Had a chance to spend some time with your family and tear yourselves away from the clear skies that we had. Yeah. One of the advantages of the dismal weather we've had for the last 2 months is that I have actually had a chance to catch up on some of my processing as well. So, yeah, I know your story there, Eric. It's good. So, one of the things I wanted to shoot this fall when I could tear myself away from Able Galaxy clusters was a little wider fields of view there. So spent a little time on the Milky Way and just in the region. Where's the controller here? Just in the region of the Summer Triangle. There you can see Deneb and Vega and Altair down there. This is a beautiful region. Many of you are, of course, familiar with this. Even with binoculars, not even just doing imaging, but with binoculars, this is a gorgeous region from here down towards Sagittarius, of course. But I've always been fascinated, certainly by this area here with the North American Nebula and the various nebulosities that we have. So I decided to run a sequence on this and get a little closer to this. So this was shot with just a Canon 60DA and a 16mm lens on a tripod, actually, just a series of individual shots. They were a series of 12 images that I stacked that were only 30 seconds long each, so didn't actually even need to track them too much. They turned up pretty well there. So, but the subsequent shots, we get zoom in closer and closer to the North American Nebula there, and those were all, of course, tracked. So the next image shows the outlined field there. And you can see it's as Alan was saying, there's lots of stars out there. I mean, it's just littered with stars, especially in that region. But again, you can see the emission nebulas punching through the North American Nebula and the Pelican there, and numerous nebulas dotting in that region there, and that of course is the bright star Deneb. So the next image. This was taken with the 60DA and a 50mm lens, so just a regular 50mm lens. The next image was a 200mm telephoto lens, and it cuts in a little closer on the North American. So there's the North American. This is a combination of regular RGB data plus hydrogen alpha data. So I shot a sequence of 12 6-minute shots, just regular RGB, and merged that with a stack of 13 10-minute shots that were hydrogen alpha filtered. The region is rich in hydrogen alpha emission, and so it was nice to be able to layer that data over the RGB data for a sort of an expanded view of the nebulosities that exist there. But beautiful structure there, and of course you can certainly see why it's commonly known as the North America Nebula. The shape is rather distinctive. Sorry, oh yeah, the pelican is there. You can see his beak there, the eyes, and the body there. And he stands up quite nicely too. So again, that was with a 200 millimeter lens. The next shot, of course, because I can't resist, I'm a magnification junkie, as you've probably gathered. I can't resist. The next shot outlines that area, which I've always been fascinated in. It's in fact the richest nebulosity within the North American Nebula there. And so I turned my my 7-inch Maksutov Newtonian, which has a focal length of 1,000 millimeters, on that with the Canon 60DA and photographed that. So you can see the Gulf of Mexico region there, if you will, Florida there as well. This is the thing that I was really after. I love this structure. This is called the Cygnus Wall, and it's an emission nebula as well, part of the North American Nebula. But it's very dense. You can see there's a lot of dark nebulae there. These undoubtedly contain star formation, even as we speak here today. This is actually sculpted, this W-shaped wavefront is actually sculpted by the bright stars in this region. So the energetic radiation coming off those very hot, massive young stars is actually sculpting that Cygnus wall and giving it that very distinctive structure. So this is a combination, again, of about 12 images at 5 minutes each, and again taken with the Canon 60DA. So yeah, Cygnus Wall, North American. That's what I've got for you. Take care, and see you again.
So we're going to finish off our evening beautifully. So, Estelle's pick of the month is called The Great Copernicus Chase by Owen Gingerich. And what it is a series of articles about major events in astronomy. So I think the first one is about like Stonehenge, and then it goes up to Einstein, it goes up to very recent discoveries. So that's what it is articles from newspapers, from journals, and apparently there's lots of illustrations, so it's good for kids too. And I'm going to read just a quote that I found online that I think describes it well. The curious reader will learn of the origin of the zodiac, Islamic astronomy, fake astrolabes, the foundation of modern astronomy in the USA, and the discovery of the spiral arms of our galaxy. So it's basically like a dummy's guide to the history of astronomy. It's a beginner's guide. So might be worth checking out. So the membership, as usual, regular membership, $75 for the year. Youth memberships are $45 for the year. Membership benefits include the Stan Mott Library, where we feature a book every month. We have the Ted Bean Lowen Library, where you can take out a telescope. I think it's $10 a month, and then $50 for an indeterminate time. You also have access to the grounds of the Fred Lossing Observatory. And you get these publications. I believe the journal is just electronic now. But you do receive astronotes as well, and the Observer's Handbook electronically if you wish. Club information. And as usual, the meetings are live streamed on Ustream. And just a few days after the meeting, you can go check them out on YouTube as well. So thank you, audience 112? Wow. Yeah, for January. Okay, so thank you to everyone who spoke, and we'll be meeting you. Oh, of course, the calendars are still for sale. And so we'll be meeting you at Gracie's if you'd like. That's just down Ogilvy Road. I believe you go down Aviation Parkway, turn right, and you can't miss it. It's right there.
But watch me try.
So I just want to give a quick note about the next meeting because I'm super excited about this. We have Professor Nick Cohen, who's coming over from McGill, and he's going to give a talk on exoplanets. And so he's a researcher. He was there making the discovery, so this guy knows what he's talking about. This is a talk that I have seen before, and so I can promise you it's excellent. It's very interesting. You do not want to miss this. All right, so next meeting, February 3rd. Don't miss it. If you have ideas, suggestions, anything, you can write me at that address. So thank you. Have a good evening, and I hope to see you at Gracie's. So I'm going to pick out the door prizes real quick. We have a few tonight.
Say goodbye to everyone on the way.
Goodbye. Have a good night.